Hi, this time I'm going to talk about the earthquake or like why structure fails, the reason behind it. So welcome to the first part of my series why structure fails, and this is Reshma from SNS institutions from civil engineering department. So today we aren't able, I mean, talking about bad concrete or rusted steel, but I'm going to talk about like something more spectral or more important, like the invisible forces of nature. For the next few minutes, I'm going to deal with why a building that stands perfectly still on a calm day or might suddenly behave like a living or like it can be breathing kind of thing when the wind blows or the earth shakes. So, as engineers, our job isn't just to fight against gravity, it's to understand the like rhythm of the world, so-called this earthquake. So let's dive deep into that. Uh, the first year of engineering that we learn about these kind of static loads. So these are very easy. It's the weight of the steel or the decks or the people itself that is called as static loads. We are, or else we can call this static load as dead load. Okay. And there is another load called live load. It pushes down straight down. The gravity is down. But nature doesn't always like push down. It pushes sideways, it pushes in pulses. These are known as dynamic loads. So think of a static load like a person standing on a frozen lake. The ice just has to be thick enough to withhold its weight. So a dynamic load is like the same person jumping up and down rhythmically like it. So how much that ice thickness must be to withstand with that weight of the person. Suddenly it's not just about weight, it's about timing sometimes, energy sometimes. When the earth moves, it not just adding weight, it's injecting energy into that system. So the concept of natural frequency, every object in any room, and every skyscraper in the world has a natural frequency. So this is the rate at which an object wants to vibrate if you disturb. Think of a guitar string. When you pluck it, it vibrates at a specific note. That note is its natural frequency. Building do the same thing. A short or in short, stiff building vibrates very fast with high frequency. A tall, flexible skyscraper sways slightly or slowly in low frequency. So, as a designer, you must know your building's notes. Like before you every break of the ground, like in earthquake, because if the environment plays the same note, you have a problem. So to know about that frequency, we have to study about something very important, which is called is resonance. So this brings us the most dangerous word in the structural engineering. Actually, it is resonance. Resonance occurs when the frequency of an external force like wind or like seismic waves matches the frequency of the structure. That is known as resonance. Imagine pushing a child on a swing. If you push at random times, the swing goes nowhere. But if you push at the exact moment, the swing starts move to away from you. The amplitude increases then. Each push adds to the last one. In a building, resonance causes the swaying to grow larger and larger with every pulse of energy until the material simply cannot stretch any further and snaps. So here is a small one kind of case study. As you can see in the picture, it is Tacoma Narrows Bridge. The most famous example in history about this resonance, the Tacoma Narrows Bridge, which occurred, that tragedy occurs in 1940. It was a beautiful, slender suspension bridge. But on a day with relatively modest winds, only about 42 miles per hour, it began to twist violently. This wasn't just the wind blowing it over, this was aeroelastic flutter. The wind created vortices that matched the bridge natural twisting frequency. So what happened to the bridge? Like it turned the bridge into a giant wing that flapped until the steel cables snapped. It taught the world that stiffness isn't just about carrying the weight, it's about aerodynamic stability. So from this, we can able to tell that frequency resonance is very much important. As a builder, we have to know the rhythm of our buildings. Thank you. We will see on the next video.